Okay, 4 into minus 2. So methods to represent signal flow graph. So how we are going to represent or what are the methods that are used to represent a signal flow graph? First one, from the system equations. That means by taking the system, they are going to give us some system equations. By making use of those system equations, we need to draw a signal flow graph. So first one, represent each variable by a separate node. So suppose if they have given V1, then make a V1 as a separate node, V2 separate node, V3 separate node, V4 separate node, like that. So use the property that value of the variable represented by a node is an algebraic sum of all the signals entering at that node to simulate the node. That means we need to draw, or we need to identify, we need to represent all the nodes that are coming towards that particular node. So coefficients of the variables in the equations are to be represented as a branch gain joining the nodes in the signal flow graph. Coefficients of the variables, suppose for example Vi is equals to 4 into V1 is equals to 4 into Vi, for example. I'll take the example. For example, they have given that V1 is equals to 4 Vi. So I need to represent this one in terms of signal. So what is my output? This is let it be. This is my node. That is my input Vi, and this is my another one. That is V1. They have represented V1 is equals to 4 Vi. Therefore, this is my coefficient of Vi. That is 4 Vi. So coefficients of the variable in the equations are to be represented as the branch gain. So this is my branch gain joining the nodes in the signal flow graph. So next one, show the input and output variables separately to complete the signal flow graph. So in order to show input and output separate, we need to show input and output separately in order to draw the signal flow graph. For example, here they have taken, consider the system equations V1, V2, V3 and V4. Here let it be. I'll draw again. Though it is there, I'll draw again. This is my Vi. Let it be Vi. That means input. And I have taken V1. We have V1, V2, V3, V0. V2 and V3, finally V out or V0. First of all, they have given V1 is equals to 2 Vi plus 3 V2. So 2 Vi, this is 2, okay, plus 3 V2, so 3 V2, that means I'll write like this. This is my 3 V2. Okay, so coming to V2 equals to 4 V1 plus 5 V3 plus 5 V3. So here the arrow representation takes a very vital role. That means either it may be whether it is moving towards that or away from that, which should be mentioned. And 2 V2. So V3 is equals to sorry, this is 5. Sorry. Okay. Okay. So see here, V2 is equals to 4 V1 plus 5V3 plus 2V2. That means it needs to be self looped. So self loop, that is here the value is 2. So 2V2. Coming to the V3, V3 equals to 5V2 plus V0 plus V0. That means can write like this. So let it be 1. So V3 equals to 5V2 plus V0 and V0 equals to 6V3. 6V3. Okay. So they are going to give us some equations, and by making those equations, by making use of these equations, we need to draw the flow, we need to draw the system. So let the output be V0 and the input be Vi, where V1, V2, V3 are the system variables, and by making use of these equations we are going to draw the circuit. From the given block diagram, name all the summing points and takeoff points in the block diagram. Represent each summing point and takeoff point by a separate node in the signal. Connect them by branches instead of blocks, indicating block transfer functions as the gain of corresponding branches. Show the input and output nodes separately if required to complete the signal flow graph. Okay, so here by making use of these equations, we are making that name all the summing points and takeoff points in the block diagram. Here we are naming each and every summing point, that is V1, V2, V3. Okay, and represent each summing point and takeoff point by a separate node in the signal flow graph. Here they have a node 1, let it be node 1, node 2, node 3. Okay, connect them by branches instead of blocks, indicating block transfer functions as the gain of corresponding branches. Show the input and output nodes separately if required to complete the signal flow graph. For example, here they have given a mechanical system like this. Sorry. So by using this mechanical system, we need to generate a signal flow graph. So here, as R of S is my input, I have taken my input, and C of S is my output, I have taken output node. So based on summing points, I have removed the summing points and make them as nodes. Okay, and make them as nodes. See here, I have made this summing point as S1 and S2. S1 and S2 are my summing points, and G1, G3, G2, H1, G4 and H2 are the ideal blocks. So I need to change them like this. So input is R of S, as I have taken its gain value is 1. It is coming to the summing point, and I am making the summing point as S1. From this summing point is going to G1, and from terminal 1 it is moving to G3 as well as G2. That means it is moving towards the second summing point in the forward path, and it is moving towards the second summing point with a forward path. Therefore G3 and G2 is coming to connected to the summing point S2, and the output of this S2 is given to the G4. As we have a negative feedback, that means from T2 terminal we are drawing back to S2 with a negative sign, that is a minus H2. I repeat, in the summing point S2, here we have positive path as well as negative path. So in forward path we are connecting G4 to terminal 2, T2 terminal, and from this T2 terminal we are giving a negative feedback to the summing point with H2, that is minus H2, and the output and the terminal T2 is connected to the output, that is with gain of 1, and this output or this terminal T2 is given as feedback to the S1 with a negative feedback, therefore minus H1. Okay, minus H1. So by taking these things, it will be some complicated. So by using this we are going to lose some time. So in order to adjust or in order to cut the time, there is a formula we are going to use, that is Mason's gain formula. So in the block diagram reduction, we are always draw the reduction blocks for the overall transfer functions. We are going to reduce or we are going to draw the transfer functions, but it takes more time to process. So it is required more time to find out the overall function. That means overall transfer function after using block diagrams. Next compressing. It takes a lot of time to find the overall transfer functions. So in signal flow graph, once the signal flow graph is obtained, direct use of one formula leads to the overall transfer function. That means by drawing the signal flow graph, we are going to use only one direct formula so that the transfer function can be identified easily. This formula is stated by Mason, and hence it is referred as Mason's gain formula. So this formula is stated as, therefore it can be represented as overall transfer function is equals to sigma Tk into delta K by delta, where K is the number of forward paths, Tk is the gain of the forward path, kth forward path. How many number of forward paths here? K is number of forward paths, Tk is the gain of the kth forward path, and delta is the system determinant to be calculated. So system determinant to be calculated. How we are going to find out the system determinant? It will be equals to 1 minus sum of individual loop gains plus sum of gain products of all possible combinations of two non-touching loops minus sum of products of all possible combinations of three non-touching loops plus sum of products of all possible combinations of 4 minus 5, like that, so on. Okay, therefore delta K can be, delta K is equal to delta, that means delta for that part of the graph which is not touching the kth forward block. We need to find out this delta. So delta K means which is not touching the kth forward path. By using this formula, we are going to reduce the time to calculate or to find out the overall transfer function. Thank you. We'll meet in the next class with the problem of this Mason gain function.